Hi everybody, and here is the lesson on areas in between curves. It's going to be pretty intuitive because we already know that a definite integral gives us the area under a curve towards the x-axis. But we can extend that idea into finding the area that goes in between two curves that we've got graphed in the coordinate plane. So with a couple modifications, we can look at the idea of a definite integral from just under a curve to in between curves. All right, so the area in between curves, if you have one function that is larger than another throughout some constant interval, and both of those functions are continuous, then you can just simply take the difference between the two and a definite integral to find that area. That's pretty intuitive to do. Now, looking ahead down here, it says, representative rectangles are used throughout this chapter in various applications of integration. So we can have a vertical rectangle of width dx, and that implies integration with respect to x, and a horizontal rectangle of width dy implies integration with respect to y. Now that's a little bit different, and we'll look at that a little bit later on. But first, let's just jump in with the first example here. And this first example indicates that we are going to find the area of the region bounded by the two curves y is equal to x squared plus 2, y is equal to negative x, and a couple of vertical lines, x is equal to 0. You know it better as the y-axis, and the line x is equal to 1. So I've got the privilege of Desmos for this, but in your case you're going to want to make sure you've got your dirty dozen down pretty cold in order to be able to sketch graphs that will help you out. So just to kind of help the cause here, as I go to graph these things, I'm going to just kind of remind everybody that this one is y is equal to x squared plus 2, and the blue one down here is going to be y is equal to negative x, and then of course we've got x is equal to 0, also known as the x-axis. And then if I could just maybe sketch in very lightly x is equal to 1, the area that we are looking for is in here. This is the area that we're a little curious about. And it's even going to extend down below the axis, as you can see there, into quadrant number 4. So that's going to help you to kind of decide what we're looking at here. Now, the good news is we already have a pretty good idea of what the situation is. You've got two continuous functions. One is always larger than the other on the given interval. So this is going to be pretty easy to set up. It's going to be the definite integral from 0 to 1 to represent the boundaries there. And then since this is the larger of the two, I'm going to write this one first. And then I'm going to have to put in my second function, which of course is the lower function, negative x. And then of course I'm going to have to tack on a dx for good measure. Alright, now I'm going to go ahead and let you know that at this point you can probably do this one on your own without too much trouble. I'm going to zip right through it here. Distributing that negative and getting everything nice and organized gives us this x squared plus x plus 2. And now I want to take an antiderivative, so I'm going to get 1/3 x third plus 1/2 x squared plus 2x, all evaluated at 0 and 1. Now, I've told you many times that you want to be careful about plugging in 0 into an antiderivative because you're not always going to get 0. Well, in this case you are, so I'm just going to zip through and say we're going to end up with 1/3 plus 1/2 plus 2 times 1. And when you go ahead and mash all that together, it becomes 2 5/6 as your area that is in between the curve. Now, I suppose if you really wanted to get technical, we are looking at square units here, but that's the basic idea of how you find the area in between two curves. So let's go to another example here. And as I go to the example on the next page, you always want to draw your graph with an appropriate shaded region, write your integral, and then solve by either using the fundamental theorem of calculus, and to be specific, we're probably looking at part 2 here, the part where you have to do the substitution in on the antiderivative. Or sometimes a calculator is really helpful to do this problem if the antiderivative can't be found using the fundamental theorem, or you have the privilege of being able to do so. Let's take a look at this next one. So we've got, once again, I've already kind of taken the liberty of doing the graphing here, and you will notice that the red curve is the secant squared graph. And then, of course, we have our dear old friend, the sine function down there. And then this line right here is x is equal to pi over 4. And then, of course, I've got x is equal to 0. So as I'm kind of sketching this out and looking at this, this is the area that we're interested in picking up. So getting the integral, once again, not too much trouble. Let's get the right tool here. That might help the cause. There we go. Okay, so it's going to go from 0 to pi over 4. And since secant squared is going to be the curve that's always on top, I'm going to start with that one. And then the sine x is always below, so that's my lower curve. It's always kind of like farther minus nearer. I think that's probably a pretty good way of thinking of this, is farther minus nearer. And you'll see what I mean by farther minus nearer before this video is over. All right, so zipping through the antiderivative here, we already know this is tangent of x, and we already know that this is antiderivative of sine is negative cosine. So the negatives wash, giving you a cosine there. All right, now this is where we're going to have to be a little cautious, because we have to make sure that we put in the right stuff. This is pi over 4, actually. I'll make sure we get it right here. All right, so if I sub in pi over 4, tangent of pi over 4 is 1, cosine of pi over 4 is root 2 over 2, of course. And then I'm going to have to subtract off for subbing in 0, and the cosine of 0 is, of course, 1. So when all of this washes out, you're going to end up with root 2 over 2 square units of area in there. So pretty easy to do. All right, let's jump down and do this next one here, and you'll see that you can find that area in between curves pretty easily on an interval from 0 to pi over 6. So once again, I've just kind of used Desmos here, quite honestly. But again, I can't imagine that this is something you wouldn't be able to draw on your own without too much trouble, given all your knowledge. So here's the area I'm interested in. And if you will notice, it is the cosine curve that is always going to be larger. And again, this is your knowledge of the dirty dozen that's really kicking in here. So you're going to be able to go from 0 to pi over 6 of cosine of x minus sine of x. And again, this is all with respect to x. So pretty easy to do. Antiderivative sine x. Antiderivative of the sine is negative cosine, so it's sine x plus cosine x, evaluated at 0 and pi over 6. So sine of pi over 6 is 1/2. Cosine of pi over 6 is going to be root 3 over 2. And then for the bottom part here, we've got sine of 0 being 0 and cosine of 0 being 1. So once you kind of combine everything and get everything down, you're going to have root 3 over 2 minus 1/2. I'm going to go ahead and leave that exact. And that's our answer for this particular problem. All right, now zooming over to the next page here. Sometimes you get curves that intersect in two parts. And sometimes two graphs do not intersect, like we've seen before, where one is just strictly larger than the other one. And this is a little bit more of a common problem here, where we've got the intersection of two graphs and a region bounded by two intersecting graphs, I should say. And you need to be able to calculate the values of A and B. Now, fortunately for us, we've already got something in our toolbox that allows us to do that. And you know full well at this point that if you want to find the ordered pairs, where two curves intersect in the plane, it's equivalent to solving a system of equations. Now, fortunately for us, this is going to be a pretty easy problem to solve. If you really don't have the ability to do this efficiently on Desmos or on your calculator, if you're kind of stuck without it for whatever reason, you can still just simply solve a system by setting the curves equal. Okay, so we're going to have 2 minus x squared for the red curve here, and then the blue one is going to be negative x. All right, now if I'm solving this problem, I'm going to try to get it into a quadratic as efficiently as I can, and that's going to mean shoving everything over to one side. And you will see that this thing factors pretty doggone fast into x is equal to 2 and x is equal to negative 1. So, and solves, I should say, factors and solves into that. So what we need to do is we need to go back and get the ordered pairs that represent these two spots. And the way we're going to do that is we're just simply going to put them into the points, or put them into the functions. I'm going to take the easy way out. I'm going to put them into negative x, because that's going to allow me the opportunity to get an answer really fast here. So now that I know that those are the ordered pairs, negative 1, positive 1 is up here, and 2 and negative 2 is down here. And if this is the area that I am interested in between these two curves, I know the red curve is always greater than the blue one on this particular situation. So all I have to do is just set up my integral just like I've done before. Let me clean that up just a touch here. And the only thing I need to fill in is going to be my limits of integration, and that's going to be really easy to do because I found those when I solved the system. The lower limit of integration is going to be negative 1, and the upper limit is going to be 2. So now I can just kind of begin this process all over again of cleaning everything up. So I'm going to have negative x squared plus x plus 2 dx when I distribute the negative and bring order to the proceedings. So this is negative 1/3 x third plus 1/2 x squared plus 2x evaluated at negative 1 and 2, which is going to mean I'm going to have to be a little bit more careful here. So I'm going to zip along here and just try to get this done as quickly as I can. This is going to be plus 2, and then that's going to be plus 4. And then when I put in the negative 1, I'm going to have a negative 1/3. Oopsies. Let's get that cleaned up. Negative 1/3. And then I'm going to have plus 1/2, and then I'm going to have a minus 2, which means I'm going to have to really, really be cautious here on putting things in. Excuse me, that should be a plus. All right, so I'm going to wind up having, all right, well, let's see what I've got here. Let's just kind of clean house a little bit. This is going to be 6, and then this is going to be minus 1 1/2, but then this negative sign will take care of that. So insofar as the things that I've combined in red, it looks like I'm going to have 7.5. Okay, and now I notice if I look at my fractions, my negative 8/3 and my minus 1/3, that's going to be negative 9/3, which is going to combine to negative 3. So it looks like my final answer here is going to be 4.5 square units when we're all said and done. Bit of a mess, but we got the job done. So again, the big catch here is going to be when you have two intersecting curves, you will need to use a system of equations to find where those points are. And yes, I will want to be able to see the work on that. All right, let's see if we can go down to this trig one, which is kind of fun too. Okay, now with this trig one, this is also an interesting problem because the sine and cosine curves intersect infinitely many times, which we all know, of course, and they create regions that produce equal areas. Well, that's just sort of the beauty of the symmetry of the sine and the cosine function. So as I'm highlighting in yellow here, this is the spot that we're interested in if we're trying to find the area of one of those regions. So now it becomes a matter of just simply identifying where those ordered pairs are of intersection here. And you kind of have to ask yourself, at what 2 points are the sine and cosine equal? Well, one of those has an x-coordinate of pi over 4, because the sine and cosine are equal at root 2 over 2 at that spot. And they're also equal at 5 pi over 4 for negative root 2 over 2. So those are going to be my two x values in terms of my limits of integration. I'm not going to really worry about the y values because they're not all that important to me right now. But it is kind of interesting to have that info at your disposal. So let's go ahead and set up the area of integration here, pi over 4 to 5 pi over 4. And you will notice very quickly it's the sine function that is first. It is the upper function, and then the cosine function is the lower one. And I'm going to hit the pause button here and zip through the integration. And you might want to hit the pause button on your video right now and run through it yourself, and then we'll check the answer here in a second. Okay, and as I reveal my work here, you will notice that I get 2 root 2 units squared. So hopefully that jives with what you had as an answer. So if two curves intersect at more than 2 points, then to find the area of the region, you need to find all of those points of intersection. That's going to be a big thing, finding all those points of intersection. And check to see which curve is larger than the other. So let's take a look at an example of that real fast. Whoopsies. And here it is right here where we have the graphs of these two functions, 3x to the third minus x squared minus 10x. That would be the red one, is what we're looking at here. And then the blue parabola, of course, is negative x squared plus 2x. All right, well, now we've got a real fascinating problem because we have multiple points of intersection here, as you can see that I've just highlighted on the graph itself. Now, as I go to want to find the area in between these two curves, we really have to break this up into two problems because during this part of our interval, we know that the function is bigger is the cubic, the red one, and then in between these 2 points of intersection, it's actually the blue function that is larger. So I'm at least going to set this up. I'm going to let you solve it out on your own and get an answer here in a moment. But let's go ahead and set it up. And according to what we need to do, we need to find the points of intersection first. So that's going to require a system of equations. So let's go ahead and get that set up using our 3x to the third minus x squared minus 10x. And let's set that equal to negative x squared plus 2x. All right, now, if my math is right, I just need to pull everything over and get that dealt with, and it shouldn't take really too much effort at all to pull that off. So what I'm going to wind up with, oh, well, that's convenient that the x squareds are going to cancel out. I'm going to end up with 3x cubed minus 12x is equal to 0. And I'm just going to factor out a 3x because that just seems like the logical thing to do. And I'm going to end up getting something that is almost a little too pleasant for my own good when I factor that difference of squares. I'm going to have an x value of 0 for that part right there. I'm going to have an x value of negative 2. And then I'm going to have a x value of 2 on this right side. So, now that we know what our limits of integration are, we can go ahead and set this up. So, I'm going to highlight over here once again, here on the left side where the red area is, where the red curve is larger than the blue one. I need to set up a limit of integration going from -2 to 0, and that's going to be the red curve minus the blue curve. And this is all with respect to x. So I'm just going to put a box around this in red and just kind of point to the fact that this is all going to be going to the red area right here. Okay? So hopefully that helps out. Now what I need to do is I need to add on this other area in between curves, and that's going to be the part that's in blue, which is going to go from 0 to 2. And then what I need to do is just reverse the order of integration here. So negative x squared plus 2x goes first, and then the cubic goes second. And again, this is all with respect to x. So as I go to do this, I'm going to box this off in blue. Hopefully you can see that. And then you will note that this goes to the blue area right there. All right, I'm going to let you finish that one off on your own to check the answer. And you can expect to possibly go over this one in class as something we're looking at here. Pretty cool example. Okay, moving ahead. Whoopsies. All right, and sorry for the technical difficulties there, but on example number 3, I want you to go ahead and try that one on your own. All right, let's move ahead to the next page. And sometimes we need to find subregions to help us find the area. And it might help us to note that we have maybe a situation like we do here, where we've got a couple of different boundaries at work. Now, if I want to find the area of the region in the first quadrant that is bounded above by root x and below by the x-axis and this line of y is equal to x minus 2, what you will notice is that I can split this into 2 regions. So to just kind of give you an idea of what it's going to look like here, when I hit this point right here, something changes. In this particular blue area that I'm shading, it's the graph of root x that is a very simple, straightforward integration to find out. However, when I try to find this area, I've got the difference in between 2 curves. So I am going to have to break this up into 2 integrals, and it's not going to be all that hard to do. I just have to figure out where these 2 curves intersect, and I think you're going to find pretty easily that this is going to occur when x is equal to 2. So I'm going to have 2 integrations here. First for the blue area of 0 to 2 of root x dx. And then I have to add on from 2 to 4 of root x minus x minus 2 in parentheses dx. Okay, now something I haven't mentioned out loud too much, but when we put our second curve in, you always want to make sure you get that in parentheses, so that way you can make sure you get the correct distribution of the negative signs there. That's going to be the big key here. So otherwise you're going to get a wrong answer, and I'd hate to see that happen. Okay, so I'm just going to zip through the antiderivative here. This is going to be 2/3 x to the 3/2 evaluated at 0 and 2. And then this one over here is going to come in at, all right, let's see if I can do this pretty efficiently here. This is going to be, well, it's going to be 2/3 x to the 3/2, and then that's going to be minus 1/2 x squared, and then this is going to be plus 2x after we distribute the sign there and get that done. All right, let's go ahead and do the easy part first. What I'm going to have is I'm going to have, let's see, I'm going to have, well, what appears to be 2/3 times the square root of 8. Okay, now I'm going to bother to simplify that, and I know that this goes to 2 root 2. So what I really have here is 4 roots of 2 over 3. So that takes care of the blue part. Now I'm going to have to do the challenge of the red part here. Okay, so this is going to be, let's see if I can get this right here. 4 has to go in first. So 4 to the third power is 64. And then I've got the square root of that, which is 8. And 8 times 2 is going to be 16. So I've got 16 thirds for that part. Okay, 4 squared is 16. Half of that is 8. And then this is going to be, well, let's take a look here. This is going to be 2 times 4, which is a positive 8. So all of that, lucky for me, is going to wash out. Now I'm going to do the other part here for when I put in 2. Now, fortunately for me, when I put in 2 into this first term right here, I've already seen how that movie ends. So I know that this is going to be 4 roots of 2 over 3, and I'm noticing very happily that that's going to drop out. All right, so let's see, 2 squared is 4, and half of that is 2, and then I've got a plus 4. All right, so let's see if I can clean this up just a little bit more. All right, those are going to wash out. I'm going to have what appears to be, let's see if I can get this right here. This is going to be a plus 2 when I simplify it. So I'm going to have 16 thirds. All right, this is going to be 10 thirds right here when I combine it with the fraction. And then I'm going to have minus 4 roots of 2 over 3 from that little bit of a mess. So you can see it drops to 10 thirds in a hurry. And that's the area of that region, both the red and the blue put together. Okay, not that bad to do. A little challenging on the analysis part right at the end, the numerical part. But if you take that slow and kind of just take it a step at a time and try not to do too much, you're going to be in good shape. Okay. All right. Now, unfortunately for us, what we need to do from time to time is we need to be able to integrate with respect to y. So sometimes the boundaries of a region are more easily described in terms of functions of y instead of x. This is going to be the part where it's going to be a little bit more challenging. It might do you some good to get on Desmos and just play around with some of these graphs so you get used to them, and maybe some of the transformations of parabolas that are going side to side, left and right, instead of up and down. Okay, so you can obtain an incorrect result in the previous example if you integrate from 2 to 2, or from negative 2 to 2, because it's just simply not going to work. You're going to get something that's always positive. You don't have the same function that's positive the whole time. So if the graph of a function of y is a boundary of a region, it's often convenient to use representative rectangles that are horizontal and find the area with integrating with respect to y. So in general, you can determine the area in between two curves. If you're using the typical vertical rectangle that we've seen, then you can use, oopsies, sorry about the mess here. You can use f of x dx, but if the area is one where we might want to use y instead, then we might want to integrate a function with respect to y. Now, don't panic, it works the same way as integrating with respect to x, and let's show you how that's done. This up, whoopsies. Okay, so take a look at what we have here. This is the same problem as what we had before. So I would imagine that we already know that it's 10 thirds. Now, instead of creating a horizontal rectangle, representative rectangle for our RRAMs, instead of doing that, or LRAMs, or whatever it is, what we might do is we might create a representative rectangle that goes crossways instead. And we'll add the areas of all of those up, going from bottom to top. Okay, now that's going to take a little bit more creativity on our part to get this done. We're first of all going to have to put everything in terms of x instead of y. And when I do that, this curved function becomes x is equal to y squared. Just simply square both sides and solve for x. This other one is going to be x is equal to whatever your y is plus 2. Okay, now remember earlier in this video we said further minus nearer. Okay, so if I am integrating with respect to y, I've got to think of the y-axis as being my base instead of the x-axis. So in this case, this becomes the further curved, and this one becomes the nearer curve. All right, so the way that I would set this up as an ordered or as an integral would be very simple. I would integrate the further curve, which is y plus 2, minus the nearer curve of y squared, and this is all with respect to y, so you know the integration is going to be easy. I just have to deal with y's instead of x's. The limits of integration, on the other hand, are going to be the challenging part, because instead of using x coordinates, I have to use y values. This ordered pair right here is, whoopsies, not 0 and 2. What am I thinking? Holy cow. That's 0 and 0. And then this ordered pair is 4 and 2. So I'm going to use the y coordinates as my limits of integration. And you might see that the integration isn't all that difficult to do. It's really not that hard. Let's find out if we get 10/3 by zipping through the integration very efficiently here. I'm going to get 1/2 y squared plus 2y minus 1/3 y third, all evaluated at 0 and 2. Okay, so plugging it in real fast, 2 squared is 4, 4 divided by 2 is 2, and then I've got 2 times 2, which is 4, and then I'm going to wind up having 8/3. All right, now this is a little bit easier to handle because it's 6 minus 8/3, which, when you get a common denominator, works out to be 10/3 in the square units department. So that's really not too bad to do. The mechanics are pretty easy. Where's the challenge? The challenge lies in deciding when to do it. So I'm going to skip over to the next page, and I'm going to show you a graph where we have to make the decision on integrating with respect to y. Okay, so here's a picture of the curves. X is equal to 3 minus y squared, and x is equal to y plus 1. I would imagine that you'd probably be able to tell which was which. The parabola is clearly the red curve that you see there, and x is equal to y plus 1. That is the black curve that's going on in the line, or the black line that's going on in here. So I think the big issue here, if you want to know when to integrate with respect to y, it's actually a simple idea. If you are thinking integrating with respect to x is a good idea, just draw some horizontal lines. Now the problem is when you get to this spot right here, you will violate the vertical line test. Your function will now violate the vertical line test, and technically it's not even a function. So in order to get around that, if you ever feel that your function is going to violate the vertical line test, that's the cue that you need to integrate with respect to y. So now let me show you what we've got here. As I get rid of this, if I integrate with respect to y, you will notice that I am not going to come anywhere near violating the vertical line test in that situation. It's just going to be a lot easier to kind of shift our focus that way. So not too hard to do. Now the only question is, what are these points of intersection? How do I find those points of intersection? Well, clearly I'm just going to set the two curves equal to each other and see what happens. So I'm going to have 3 minus y squared, and that's going to be equal to y plus 1. Okay, now let's get everything on one side, and that's going to be y squared plus y, and then minus 2. And then this is going to end up being, let's see, y plus 2 and y minus 1. So y is negative 2, or y is equal to 1. I'm not really worried about the x coordinates here because that's just going to be a waste of my time. Excuse me. And if I'm going to go farther minus nearer, then it's going to be red minus black here. So let's go ahead and set this up, going from negative 2 to 1, and then the red one and then the black one. And again, this is all with respect to y. Okay, I'm going to hit the pause button right here and do the math. Catch up with me on the flip side here. Pause it and work it yourself and see what you get. Okay, so you can check my math there and see how I did. It looks like it's going to be 4.5 square units when we're all said and done. Okay, so in this example, if we integrate with respect to y, you only need one integral. If I had integrated with respect to x, I would have needed at least 2 integrals because the upper boundary would have changed at x is equal to 2. And again, I'm going to go back to this point right here where in this area you're going to be violating the vertical line test anyway. All right, let's take a look at one more example here. And as we go down to example number 6 and take a look at that, you automatically see that right in this particular part of the graph, we are going to be violating the vertical line test. So it probably doesn't do us much good to get this in terms of x, or integrate with respect to x because of that purpose. So let's take a look and see if we can figure out what's what here. I'm pretty confident that x is equal to y squared minus 2. That's going to be my purple, or my blue one. Now if I want my purple one here, I need to change this to a purple, so bear with me. This is going to be x is equal to y to the 1/3. Okay, so nearer or farther minus nearer. And I think even though the blue one goes to the left of the axis, I think what I need to do is I need to come up with the ordered pairs here. And that's going to be super messy to do. Okay, so I would almost reach for the calculator on a problem like this to try to figure out what that point of intersection is right there. And then you'd set it up accordingly. So I'm pretty sure that one of these is -1. I'm just not quite horribly confident about that other one, the way it looks. So I'm thinking maybe perhaps I might have typed it in wrong in Desmos the way I look at it. But let's see if we can figure this out here. Well, the nice part is you can just simply substitute in x cubed in place of y. But the problem is you're going to have so many points of intersection there, it's not even going to be funny. So I think we're going to hit the pause button on this one and take a look at one more example on the next page. Okay. And we'll actually cover this one in class. So that takes care of what we've done for today. Enjoy, and we'll see you soon.